Welcome to section 8.5, and we're adding another test for series convergence or divergence to our list. This one is more specific. This is for alternating series test. So you know how we were talking about limit comparison is good for fractions? Well, alternating series test is only going to work when you are working with an alternating series. So you have some kind of a negative inside parentheses with a power on the outside, so it's going to alternate back and forth. Now, with the alternating series test states that you will be convergent if, number one, the limit as n approaches infinity of that nth term is equal to 0. If that's met, then number two, the n plus 1 term has to be smaller than the nth term for all n's. Okay, so both of those have to be true. If both of those are met, then you are convergent. If for some reason number 1 is not equal to 0, then you can go to your nth term test, which states if it's not equal to 0, okay, you can use that one to show your divergence. Alrighty, so let's see what's going to happen. On number 1, I can see that this is an alternating series test. I see that little -1 right there. So the first step I'm going to do is show that my limit as n approaches infinity of the non-alternating part, that equals 0. Well, if I put in really big numbers in the denominator, this fraction is going to get smaller. It is going to go to 0. So we have just passed step 1. Step 2, my n plus 1 term has to be less than or equal to my nth term. And sure enough, if your denominator is bigger, you're going to be smaller. Therefore, my series, wow, that is a terrible sigma notation. But I know we all love each other for our personalities, not for our ability to draw. So we passed step 1, we passed step 2, therefore we converge. Okay, so let's look at another example. This is pretty nice. Okay, now once again I have that -2, so that shows me that I do indeed alternate. Now you may want to rewrite it with that -1 on the outside, and that way you have your n over 2n minus 1 power. You don't have to rewrite it, but I do want you to think about separating that out, because you're just taking the limit as n approaches infinity of the n over 2n minus 1 part. Well, if I look at the infinity, I'm going to get infinity over infinity. So I take the derivative. I'm going to use L'Hopital's rule. Well, the derivative of n is 1. The derivative of 2 to the n minus 1 is natural log of 2 times 2 to the n minus 1. Now when I plug that in, I get 1 over a really big number. That's going to 0. Okay, so by L'Hopital's, Okay, so now, number 2, I need to show that my n plus 1 over my 2 to the n minus 1 plus 1, or n, I need to know that that is less than n over 2n minus 1. Now, if you can't see it right off, you may need to do some manipulation here. I know that this guy right here on the bottom, that's the same thing as 2 to the nth times 2 to the -1. Well, that 2 to the -1 power is 2. Okay. The bottoms are the same. We know that n plus 1 is less than or equal to 2n, because remember, n starts at 1, so that would be 2n. Or that would be 2, that would be 2, they'd be equal. When n is 2, this is 4, this is 3, and it is less than. So we know for a fact that n plus 1 over 2n is less than or equal to n over 2n minus 1. Therefore, we know by our alternating series test that our series we started with, and always write it without the manipulation, we know that that converges as well. Okay, we had to do a little bit more work there. Let's see number 3. All right, so number 1, I'm going to be looking at the limit as n approaches infinity of n squared over n squared plus 5. Okay, well, that's going to equal 1. That does not equal 0. Okay, so it doesn't equal 0. This series right here, okay, follows under that nth term, so it diverges. Okay, now we can't just go right to it. We do have to state another test that will work. Now number 4, when I look at this, it's almost like, well, wait a minute, this doesn't look like an alternating series test, okay, or an alternating series. But if I put 1 in there, I'm going to have the cosine of pi, which is -1. If I do n equals 2, that's going to be the cosine of 2 pi, which is +1. n equals 3, that's going to be the cosine of 3 pi, which is -1. Oh, this guy right here is our alternating factor. So this guy is actually going to be 1 over n times -1 to the nth power. So it is an alternating series. I just need to show that the limit as n approaches infinity of 1 over n is equal to 0, and it is. And then 1 over n plus 1 is less than or equal to 1 over n, and it is. So therefore, my original series, now even though we know these are equivalent, I want to rewrite it as it was given and state that that converges. So if it doesn't look like an alternating series and you have sine or cosine in there, you might want to check it out. It may indeed be an alternating series. See you back in class.